Thevenin-Norton equivalence. The Thevenin-Norton theorem provides a new conceptual technique in solving complicated circuits. The theorem is fairly straightforward when written down. But the process of applying it is long and tedious. These equivalents ideas are a conceptual leap in viewing everyday circuits. Like a power supply. A power supply is a really good way of viewing a Thevenin equivalent. The idea of the Thevenin-Norton equivalent is, or maybe not equivalent, I should say theorem, is to identify and separate the load circuit of interest from the remainder of the circuit. This subcircuit is called the Thevenin or Norton equivalent. So picture-wise, I see two components of the circuit. So I have a circuit here. And what I've done here is that I look at the circuit and what I see here is that there is a load someplace. So let's say that this is my load. So what I tried to say in words is that now I have a load circuit that I've identified, and here is my load where these guys are connected between two terminal points that we call A and B. So this guy here is the subcircuit. So our goal here is that when I look at that subcircuit, it can be quite complicated. So the subcircuit is typically complicated, sometimes very complicated, and is removed from the load. So now we have two separate pieces. And when I look at the load, what we want to do with the load here is calculate the current or voltage of the load. So now that we removed it, one uses the Thevenin-Norton theorem to convert it into a Thevenin or Norton equivalent. So picture-wise, we say the following thing. If I convert it using Thevenin's theorem, we call it a Thevenin equivalent. So that means here, if I come over here and let's say that I copy this, so if I bring this down here and I repaste it here, I could have a circuit, and then this guy is now replaced with the circuit that reads a voltage source and a resistor in series, where these nodes are A and B. If I do a Norton equivalent, then it looks like this instead. We have our subcircuit, and this is now replaced with a current source in parallel with this resistor. So with that in mind, one now reconnects the much simpler equivalent to the load circuit and solves a much easier circuit. So in other words here, I have this situation. I have a load. And so if I look at a Thevenin circuit, I have a load that looks like this. So here's my load right here. So now if I take this guy here, see if I can grab all of this. And then if I copy this one right into here, well, I'm not going to copy it actually. I'm just going to draw it. So this will be a voltage source with a resistor connected to here. This is a considerably easier circuit, right? This is a considerably easier circuit. And if I was to do it with the Norton, I have effectively the same type of thing here, where now my Norton circuit now looks like this. Yeah, let me see if I can copy this and paste it. So if I come over here, I then do effectively the exact same thing, where now I reconnect this, and you can see here that this is a much easier circuit to solve. That's the idea behind the Thevenin or Norton theorems. Here are the rules of Thevenin's or Norton's, the Norton theorem. Now, I'm just going to use an image to just show you the rules here. So let me paste this in here. And so whether I call it the Thevenin rules or the Norton rules, it's exactly the same. So it says the first thing you do, part A, is that you determine VOC with all sources activated. If the open circuit contains sources around the open, apply KVL around the open circuit to determine VOC. Use any method to solve for VOC. That means use any of the techniques that you use up to this point to calculate that. B, determine RTH. And it turns out that there's two methods. We're mostly interested in method 2, but I do want to use method 1 because it only applies to independent sources. And this is more of a conceptual approach, which will be very powerful when we deal with RC and RL circuits. So in this situation, you deactivate all the sources and determine RTH relative to the terminal points AB. Method 2 is the most important one because it includes not only independent, but dependent sources. This is how we want to calculate it. You place a short at the terminal points AB and calculate I short circuit using any method. Then we determine RTH using RTH divided equal to VOC divided by I short circuit. And then we redraw the Thevenin equivalent circuit and we solve the circuit problem. So there is a couple of warnings that I want to do. Just to restate what I just stated here, it's really the example that becomes most important. And so I'm going to say warning. Method 2 is the most important method to learn for exam 1, because that's what you're going to be given. That is, quiz 4 and exam 1 will require you to use method 2, not method 1. Method 1 is solely introduced now to give one a physical understanding why these theorems are valid. The process shown above is step 1, determine VOC, which is the same as VTH. Step 2, determine RTH using 2 different methods. Method 1 what you do here is that you deactivate all independent sources and calculate the effective resistance. And what I mean by the effective resistance from the point of view of the load. So I should be careful here and say, when I say the effective resistance, this is only from the point of view of the load. That's what I mean by the effective resistance. And this effective resistance is between AB, and that's what we're going to call RTH or RN. And then method 2 places a short across nodes AB and calculate I short circuit, which is the same as I Norton. The Thevenin or Norton resistance is the combination of RTH is going to be VOC divided by I short circuit.